Hi, it's Tech Trailblazer. Welcome to our new series. Today in this video we are going to see: what is the need for optimization algorithms? What are the different algorithm optimization techniques? Bayesian optimization algorithms for differentiable functions. What is the need for optimization algorithms? The concept of hyperparameters in machine learning must first be clarified before understanding the need for optimization algorithms. The model training process deals with achieving the best possible model parameters. For example, during training the weightings of features within the model can be established. Hyperparameters, on the other hand, are set before the training process by the developer or data scientist. These are model parameters used to configure the overall learning process of the model. Examples of hyperparameters include the setting of the learning rate or the count of clusters used by the model. Optimized hyperparameters are therefore vital as it ensures the model is at peak efficiency, reducing the loss function and improving the effectiveness of the model as a whole. Each hyperparameter can be tweaked or changed until the most optimum configuration is achieved. This means the model is as effective and accurate as possible. Improve a mechanism or system by making fine adjustments. Manual optimization of hyperparameters can take a huge amount of time and resources, as a data scientist must cycle through different combinations and configurations. Optimization algorithms are therefore used to streamline the process, effectively finding the optimum configuration of model hyperparameters. An optimization algorithm will work through many different iterations to find the optimum configuration of the model, beyond what is possible by a human. Another common issue within black box machine learning is that it can often be impossible to understand the effect of hyperparameters on the wider model. In these cases, manual optimization by a developer wouldn't be possible. Optimization algorithms are leveraged to improve model configurations even when derivatives are unknown. The technique of cross-validation is usually used to test these optimized hyperparameters on new and unseen data. The process sees the model process unseen testing data, indicating whether the model is overfit to the training data. This helps to gauge the model's ability to generalize when facing new data, an important consideration for any machine learning model. As a result, optimization algorithms are an integral part of the machine learning process. What are the different algorithm optimization techniques? There are many different approaches within optimization algorithms, with different variants of each technique. Although there are different techniques, the aim is generally the same: to minimize the loss or cost function. Through optimization, the difference between the estimated and real value is reduced. Optimization algorithms use different techniques to test and evaluate combinations of hyperparameters to find the optimal configurations in terms of model performance. The algorithms are often used within the model itself to improve its effectiveness in light of its target function too. A way of grouping the many different optimization algorithms is whether the derivative of the target function that is being optimized can be established. If the function is differentiable, the derivative can be used within the optimization algorithm as a valuable piece of extra information. The algorithm will use a derivative to improve the direction or focus of its optimization. But in some cases, derivatives may not be accessible or available. In other cases, noisy data may cause derivatives to become unhelpful. Derivative-free optimization techniques are used by optimization algorithms that avoid using derivatives altogether, using just the function values instead. Optimization algorithms for differentiable functions. For machine learning model functions that are differentiable, the function's derivative can be leveraged during the optimization process. The derivative can inform the direction or selection of each iteration of hyperparameter combinations. The result is a much more focused search area. This can mean optimization algorithms can perform more effectively when compared to derivative-free optimization algorithms. Common optimization algorithms when the function is differentiable include gradient descent, Fibonacci search, line search. Gradient descent. Gradient descent is a common technique in machine learning optimization. The gradient is measured and multiplied by the learning rate hyperparameter, which is optimized to minimize the loss function. It's a common approach within the training of machine learning algorithms too. Gradient descent is in the wider group of first-order algorithms, which use the gradient or first derivative to move through the search space. Fibonacci search. Fibonacci search is a type of optimization technique in the wider group of bracketing algorithms. It's generally used to find the minimum or maximum of values and moves through the search area within a specific range or bracket. Each step in the sequence narrows the bracket of an optimum value, effectively narrowing the search area in each iteration. A similar technique is the golden section search, which again narrows its boundaries in the search for an optimum value. Line search. The line search technique uses a descent direction to iteratively refine a target function. The approach performs a bracketed search along a line after the direction of movement is selected. Each iteration will be optimized against the target function until no more optimization is achievable. It's part of a wider group of optimization algorithms called local descent algorithms. Derivative-free optimization algorithms. In some cases it can be challenging or impossible to identify derivative information of the machine learning model's function. This could be down to a significant resource expense or if the data is particularly noisy so that derivatives aren't useful. In the case of black box machine learning, derivatives may be difficult to define or identify. They can also be difficult to establish in simulation-based learning environments. Derivative-free optimization algorithms use only the values found in the objective functions. This approach is usually less effective or efficient compared to optimization algorithms that use derivatives. This is because the algorithm has less information to inform the optimization process. Common examples of derivative-free optimization algorithms include evolution algorithms, Bayesian optimization, random search, evolution algorithms. Evolution algorithms are a common approach when optimizing deep neural networks. The technique mirrors genetic or evolutionary selection processes to combine and assess hyperparameter combinations. Hyperparameters are combined through different iterations, with the most successful combinations forming each generation. Hyperparameters are combined, tested and evaluated, with each iteration informing the next round of testing. This way, each iteration becomes more and more optimized and effective, mirroring the process of natural selection. Bayesian optimization. Bayesian optimization is one of the most popular approaches for derivative-free optimization algorithms. The technique refines the hyperparameter combinations with each iteration by focusing on combinations which best meet the target function. This approach avoids a resource or time-intensive blanket approach in which all combinations of hyperparameters may be combined and tested. Instead, Bayesian optimization is a sequence of refinements, with the model selecting hyperparameters with the most value to the target function. Random searches. Random searches is a straightforward and commonly used approach to machine learning optimization. Each hyperparameter configuration is randomly searched and combined to discover the most effective combinations. It can be used to discover emerging or new hyperparameter combinations because of the randomized nature of the search. If each hyperparameter configuration is mapped to a grid, random searches technique will randomly search and combine the values. This is unlike Bayesian optimization, which is more focused in its approach when used in optimization algorithms. Random searches will usually be limited to a specific number of sequences or iterations. If left unlimited, random searches may take a huge amount of time to complete. It's generally used to find the best combination of hyperparameters, avoiding the need for any manual checks.